Welcome. Today we are going to find out how your phone really knows where you are. And by the end, you will see that the answer runs on Einstein's relativity. You open a map and a blue dot appears. It is right to within a few meters. To do that, your phone is listening to clocks flying 20,000 kilometers overhead. And here is the strange part. If we ignored Einstein, that little dot would drift the length of a whole city, every single day. Here is how it really works. So let us start above your head. About 24 GPS satellites circle the Earth, roughly 20,000 kilometers up. Each one does almost nothing. It just broadcasts a single repeating radio message. That message says two things. Here is my exact position, and here is the exact time on my clock. That is it. And one detail matters a lot. Your phone only listens. It never talks back. The satellites shout downward, and your phone quietly catches whatever it can hear. Now, how does a timestamp tell your phone how far away a satellite is? The trick is the speed of light. Radio waves travel at about 300,000 kilometers per second, so the message arrives a tiny bit late. Your phone compares the time the satellite sent it with the time it arrived. That gap is the delay. Multiply the delay by the speed of light, and you get your distance to that satellite. Timing is everything here. Light moves about 30 centimeters in a single nanosecond, a billionth of a second. So a clock error of just 1 nanosecond becomes a 30-centimeter error in your position. One distance, though, is not enough. If you know you are exactly 20,000 kilometers from one satellite, you could be anywhere on a giant sphere around it. So we add a second satellite. Now you are on two spheres at once, and they only overlap on a circle. Add a third satellite, and that circle shrinks down to just 2 points. One of those points is out in space, so the Earth itself rules it out. That leaves a single point on the ground. That is you. This method has a name. It is called Trilateration, because it finds you from distances, not from angles. But there is a catch. All of this depends on your phone knowing the exact time. And your phone's clock is cheap. It is a little bit wrong. Remember, even a tiny clock error becomes a big position error, so 3 satellites would not actually be enough. The fix is elegant. You listen to a 4th satellite. With 4 spheres instead of 3, there is exactly one combination of position and clock correction that makes all of them meet perfectly. So 4 satellites solve 4 unknowns at once. 3 of them pin down where you are. The 4th fixes the error in your phone's own clock. Step back, and you can see what GPS really is. It is not really about radio waves. It is about clocks. The whole system is a flock of flying clocks, all telling you the time as precisely as humanly possible. And ordinary clocks are nowhere near good enough. So each satellite carries an atomic clock, using cesium or rubidium atoms to keep time. These clocks are accurate to within nanoseconds, billionths of a second. The entire trick of turning delay into distance only works because those timestamps are nearly perfect. Which raises a problem nobody expected. Here is where Einstein walks in. His first idea is called special relativity. It says something that sounds impossible. A clock that is moving very fast actually ticks more slowly than a clock standing still. This is called time dilation. And GPS satellites are moving fast. They race around the Earth at about 14,000 kilometers per hour. So because of their speed alone, their clocks tick a little slow compared with ours on the ground. Over a full day, that adds up. Each satellite clock falls behind by about 7 microseconds. A microsecond is a millionth of a second. But Einstein had a second idea, called general relativity. This one is about gravity. It says that a clock sitting in stronger gravity ticks more slowly, and a clock in weaker gravity ticks faster. Down here on the Earth's surface, gravity is strong. But 20,000 kilometers up, gravity is much weaker. So out there, the satellite clocks tick faster than ours. And this effect is bigger than the speed effect. It makes each satellite clock gain about 45 microseconds every day. Notice it pulls in the opposite direction. Speed slows the clocks down, Weaker gravity speeds them up. So we have a tug of war. On one side, speed pulls the satellite clock 7 microseconds slow. On the other side, weak gravity pulls it 45 microseconds fast. They fight each other and gravity wins. Subtract the 7 from the 45, and you are left with 38. So the real result is this. Each satellite clock runs fast, ahead of a clock on the ground, by about 38 microseconds every single day. That sounds tiny. 38 millionths of a second. Surely that cannot matter. Here is why it matters enormously. Remember the golden rule of GPS? The system turns time into distance by multiplying by the speed of light, and light is fast. So a small error in time becomes a large error in space. Run the numbers on those 38 microseconds a day, and your blue dot would not just wobble, it would slide off your true position by roughly 10 kilometers every single day. That is the width of a whole city district, and it would keep going, day after day, drifting further from where you actually stand. The map would become useless within hours. So how do engineers stop it? You might think they patch the satellites every day. They do not. They fix it before launch, in the factory. They know exactly how much relativity will speed up each clock once it is in orbit. So they deliberately set the clock to tick a hair too slow while it is still on the ground. The clock's nominal frequency is 10.23 megahertz. On the ground, they tune it down to about 10.22999999543 megahertz. Then they launch it. And once relativity speeds it up, it ticks at exactly the right rate. Einstein, preloaded. Now picture the whole thing running. You are walking through a city, looking at your map. Above you, satellites sweep across the sky along their orbits. Your phone is silently catching 4 or more of their signals at once. Several times a second, it solves for those 4 unknowns, where you are and the error in its own clock. And it does it all without you ever knowing. The blue dot just stays locked to you as you turn each corner. Effortless on the surface, and underneath, a constant, careful calculation. One more thing worth knowing. GPS is actually the American system, but it is not alone. Russia runs its own constellation called GLONASS. Europe has Galileo, and China has BeiDou. They are all siblings, all doing the same job in their own orbits. And here is the beautiful part. Every single one of them must correct for the same relativistic effects. There is no way around it. The physics is the same physics, no matter whose flag is on the satellite. Relativity is non-negotiable. Let that sink in for a moment. Relativity is usually described as something exotic, the stuff of black holes, thought experiments, and chalkboards full of equations. Something that has nothing to do with everyday life. But GPS proves otherwise. Relativity is not just a beautiful theory. It is a hard, practical engineering requirement, built into hardware that is flying over your head right now. If we got Einstein's math even slightly wrong, your map would simply not work. The abstract and the everyday turn out to be the same thing. So here is the whole story in one picture. Every time you open a map and a blue dot finds you, 2 of Einstein's theories are quietly at work. Special relativity for the satellite's speed. General relativity for the gentle pull of gravity. Both measured, both corrected, both trusted, 24 hours a day. Century-old physics, running silently, just to keep you on the right street. Next time a map finds you, take a second to notice. That is Einstein, working. Thank you so much for watching and for spending this time being curious with me. I hope you never look at that little blue dot the same way again.